In order to understand the need for NAT, you need to understand a little bit about the internet. The internet is usually represented as a cloud, but if you were to pull that cloud cover, what you would see is just this networks of networks and networks. Hundreds and thousands of networks that are all connected together by routed devices and different internet service providers. Let's just say that these bunch of routers represent an internet service provider or ISP. And here is your home or business network that is connected to your ISP. That ISP is connected to other ISPs and they connect to other homes and other businesses all around the world. Now, this network in the 90s was growing so large at a very high pace that experts deemed that we would eventually run out of IPv4 addresses soon. The IPv4 is a 32-bit address containing 4 octets and can contain around 4 billion addresses. Now, if we were to connect everyone's device with the internet directly, we would exhaust the whole IPv4 address space very quickly because there just aren't enough addresses to allocate every device. So that is where NAT came in. NAT was developed to save the internet from its depleting IPv4 addresses. NAT is used for many other things, but the main reason how it got so much famous is that it allowed multiple devices like desktops and laptops with private IP addresses to share an internet or public IP address. Now, NAT is typically implemented on a device that can perform some sort of routing, like a Cisco router. Now, to understand public and private IPv4 addresses, let's have a quick look at the IPv4 classes. The IP addresses have been classified into 5 classes. Class A addresses were intended to accommodate very large networks. Class B for medium-sized networks, and Class C was intended for small-sized networks. These are the quote-unquote usable networks, meaning that can be assigned on an interface or on a network interface card or NIC. So our focus will be mainly on classes A, B, and C. Class D is for multicast addresses, which is a separate paradigm altogether, and Class E space is reserved for experimental purposes. Now that you have a brief insight into IP classes, let's try to understand which ones are public and which ones are private. Public IP addresses are publicly registered on the internet, and your device needs to have a public IP if it wants to communicate over the internet. Now, the same public IP address is also referenced as registered address, internet address, external address, or global address, which essentially means the same thing. Private IPs are, however, not registered on the internet, and any device that has a private IP cannot communicate over the internet directly and has to go through a NAT device that translates its private IP to a public IP address. Private IP addresses are also referenced as local or internal addresses. Now, you might be thinking which IPs are considered private. The experts and the powers that be created the RFC 1918, which defined the address allocation for private networks from IP classes A, B, and C respectively, reserving a full Class A block of 10.0.0.0 and 16 contiguous Class B network blocks starting from 172.16.0.0, and finally 254 contiguous blocks from Class C starting from 192.168.0.0. Now, truth be told, when it comes to public IP address space, there is no RFC that defines the public IP space like the private IP space. But we can take into account the IP reservations from the IPv4 address space, and the rest we can roughly conclude is the public IP address space. The RFC 6890 defines the special purpose IP address registries, in which some well-known reservations like the loopback address of 127.0.0/8 and the APIPA, which stands for Automatic Private IP Addressing, which your NIC gets if you have no address configured via static config or DHCP lease, that is off network 169.254.0.0/16. All the private IP address ranges from the RFC 1918 are also mentioned in this RFC. The IPv4 that we all know and love has this field in its header called the protocol field, which we will refer to as protocol numbers. It is there to identify the next level protocol. Now you might be thinking, what do you mean by that? Well, to answer that, let's have a look at the RFC 791, which defines the Internet Protocol. Jumping to the header format section, we see the protocol field, which represents the protocol numbers that we are talking about. So what are these numbers? Well, these are numbers which many of your favorite protocols of daily use. For example, the ping application uses the ICMP protocol, which the IPv4 identifies as protocol number 1. The famous OSPF uses the IP protocol number of 89. Now that you have that understanding, TCP uses IP protocol number of 6 and UDP uses 17. In turn, TCP has a bunch of ports ranging from 0 to 65,536, which also contain the well-known web ports of HTTP and HTTPS. Similar is the case with UDP. It also has the same range of ports, and some ports of UDP you may know are the Radius Authentication and NTP or Network Time Protocol. Now this review is important because you will be seeing IP addresses with port numbers from here on out. We have two computers residing on the same network. Let's say PCB is hosting a file sharing service via the SMP protocol and PCA has to access the shared folders residing on it. Now on Windows, you basically use the run application and type in the target IP address of the file server with slashes in the beginning. At this point, PCA sends an ARP request message on the network to find the corresponding layer 2 address of PCB and binds it in its ARP table after the response. PCB also does the binding for PCA via the ARP request message initiated by PCA because it contains its layer 2 address. Now SMB operates on TCB. So PCA generates a TCP source port number from its predefined source port range, which differs system to system. For example, my Windows 10 machine has a TCP source port range starting from 1024 to 65,536. Same can be checked for the UDP ports as well. Let's just say it selects the source port 1024 for this session. Now the IP packet is ready to be sent with the source IP of 192.168.10.111 with the source port number of 1024. The destination in this case will be 192.168.10.222 with the destination port number of 445, which is the well-known port for the SMB protocol. PCB gets the message and processes the required information, and the reply back is literally an inverted packet which has the source IP of 192.168.10.222 with a source port of 445 and the destination IP is 192.168.10.111 with the destination port of 1024. In case of a router in the middle between the two different networks, the only difference is in the ARP entry. Instead of PCB's layer 2 address, it requests its default gateway's layer 2 address, which in this case is the router, and then forwards the packet. Now there are three basic types of NAT that you will mostly encounter in the real world. We will cover these NAT types in a familiarization order, meaning the NAT you see almost daily to the NAT you don't see as much often. The type of translation from which NAT became famous for is called NAT Overload or PAT, because it uses source port numbers alongside source IP addresses for mapping onto a single public IP address. This is possible because of the wide range of random source ports clients can generate for each session, making each NAT session distinguishable from the other. This type of NAT is used almost everywhere for internet access, in your homes, your office, etc. from multiple devices utilizing a single public IP address. The next type of NAT you will see more common is the static NAT. This type of NAT is mapped one-to-one, meaning one single public IP with all of its IP protocol numbers, TCP and UDP included, will be mapped to one single private IP address. Static PAT is the better and scalable version of static NAT as it maps port numbers alongside IP addresses for one-to-one mappings. This is often referred in the industry as port forwarding. Now, static NAT or static pad are typically used when you are hosting some sort of service in your private network and you need it to be accessible from anywhere on the public network. The most common example of that would be if you have installed IP cameras in your home and you need to access them from anywhere via the internet. Dynamic NAT works on the concept of IP pools. You purchase a pool of public IP addresses from the ISP and map your private IP address range. So if you have a pool of 2 public IP addresses and have 3 clients residing on your private network, only 2 can talk to the internet at a given time. The third client will have to wait until one of the public IP is free. Until then, its traffic will be dropped. Note that this is not port address translation, it's a full IP protocol translation, means all IP protocol numbers are NATed onto one of the IP addresses within the public IP pool. It is very uncommon that you will see this type of deployment as public IP addresses are expensive and this design doesn't scale well. However, it works with overlapping addresses, which is a topic for the future series. Well, I hope this has been informative for you and I'd like to thank you for viewing.